Hello there, guys, and welcome to another video. Let me just share my screen fully. So yes, today is the second lesson, or should I say lesson 3, because our first lesson, I combined lessons 1 and 2 together. Today is lesson 3 of unit 2, which is all about even and odd number proofs. So let's just dive in. So today's model problem is a statement, the sum of two even numbers is an even number, always true? How can you be sure if it is always true and not just true for a few examples? So an example of a not an acceptable proof is just using inductive reasoning, right? Taking a couple examples like 2 plus 2 equals 4, 6 plus 8 equals 14, 10 plus 20 equals 30, like using a pattern to make a general conclusion. So saying something like, since these examples show that an even plus an even is an even, then this means every time we add two even numbers, it will be an even number. That is using inductive reasoning. And remember, that's what we use when talking about the turkey that was going to be also fed 3 times. But remember, we realized that day was actually going to be Thanksgiving and it wasn't going to be fed 3 times. So we actually need to figure out a general way of making a proof so we can make a general conclusion. So before we do that, we actually got to do some couple definitions. And I put places in your handout today to put down these definitions. So first, an integer. We just need to be on the same page what an integer is. An integer is a whole number from the set of negative, non-negative, and positive and 0 numbers. So it belongs to a whole number, and positive or negative, it can be considered an integer. And you see a bunch of examples here. Second thing we need to go over is the closure property. The closure property states that if a set of numbers, integers, real numbers, etc., is closed under some operation, such as addition, subtraction, or multiplication, then the performing that operation on any two numbers in the set results in the element belonging to the set. So the chart below shows that an integer is closed under addition, subtraction, and multiplication. So when you add two integers like 5 plus 7, you get another integer 12. When you subtract two integers, 7 and 5, you get another integer. When you multiply two integers, 5 times 2, which equals 10, you get another integer. Those are all fall under the closure property, but not division. For example, 5, which is an integer, and 2, which is an integer. When you do 5 divided by 2, you get a decimal. You get 2.5, and 2.5 is not an integer. So one thing we need to understand is the closure property. So now we're actually going to define what is an even number. So we will define an even number as a number that is divisible by 2, or an integer that is multiplied by 2. So for example, if we're going to call x an even number, then we must say x is equal to 2k, where k is an integer. Remember, when you take an integer and you multiply by 2, it will be an even number. So let's just see some examples of that real quick. So when we let k equals 2, 2 times 2 is 4. 4 is an even number. If we let k equal 30, 2 times 30 equals 60, that's also an even number. So that is how we're going to define an even number, when you get an integer and you multiply it by 2. So then what is an odd number? Well, we will define an odd number as a number that is not divisible by 2, or an integer that is multiplied by 2, then added by 1. So, for example, if we're going to call y an odd number, then we must say y equals 2k plus 1, where k is an where k is an integer. So let's see some more examples. So if we let k equals 2, then we'll say y equals 2 times 2 plus 1, which equals 5. And that's an odd number. Let's see, what about k equals 30? We'll say y, so that should say y, but it should say y equals 2 times 30 plus 1, which is 61. And that's odd as well. So that is how we're going to define odd numbers in our proofs. It is an integer times 2 added by 1. So with those definitions, let me stop sharing my screen and let's head to our handout for today. Give me one quick second as I share my screen. All right, sorry about that. Give me one second. Boom. So we're going to go ahead and prove that when you add two even numbers, that it will always equal an even number. So the first thing we need are two even numbers. So what we're going to do is say, let A and B equal two even numbers. So remember, we actually have to use the definition of even numbers now. So we're going to say A equals 2K. No, we're going to say A equals 2X and B equals 2Y, where X and Y are integers. And in red, so in black, I'm going to write the statement. In red, I'm going to say why we're allowed to say the statement. So why are we able to say A equals to 2X and B equals to Y? Because this is our definition of even numbers. So now we're going to go ahead and perform the act. So remember, this question is asking us to add the even numbers. So we're going to say A plus B is equal to 2X plus 2Y. And the reason why I'm able to do that, I'm just doing substitution. Right? We said A was equal to 2X. We said B was equal to 2Y. So instead of just saying A plus B, I'm going to use the definition of even numbers in our sum instead. So instead, we're going to work with 2X equals 2Y. So now we're here. Remember, our goal is to prove that 2X plus 2Y equals another even number. And what is an even number? 2 times an integer. So we kind of want to manipulate what we have here already. Oh, sorry, wrong thing. I meant to use the highlight tool. We want to manipulate what we have here already. So it shows us doing 2 times a value. So right now we're at 2X plus 2Y. And what I'm going to do is I'm going to factor out a 2. So if you notice, we're starting to see that 2 times a value. We have 2 times a value. But now this is where the closure property comes in. We already said X and Y are integers. And remember, under addition, we can apply the closure property on integers. So we're going to say, let Z equal X plus Y, where Z is an integer. And the reason why we're able to say this is due to the closure property. Right? If we stated already right here, remember, I'm going to highlight it where we made that claim. We already said X and Y are integers. We made that claim very early. So under the closure property, we can say Z is also an integer due to that. So now we're going to go ahead and substitute that in. We're going to get, now we're going to get 2X plus 2Y equals 2Z. Because we are going to substitute once again. So now that we have that 2Z, we have the definition of an even number once again. So we can say 2Z is an even number by definition of what an even number is. So we proved that an even plus an even equals an even. We didn't use specific numbers. We use mathematical definitions and theorems and conjugates And postulates, we use math facts to make this proof make sense. When you only use specific numbers, then your proof only applies to those specific numbers. But when you make a general claim and use math facts to support those general claims, then you are able to make a general conclusion that applies to all. So I highly recommend go over this video a couple times because this is going to be a very important proof that you understand. When it's even plus odd plus odd, subtraction as well, that is going to be a huge concept. As you notice, today you're going to be asked to do an odd plus an odd. So go ahead, work hard, work strong. And if you have any questions, please reach out. Until then, welcome to Mr. Morales Academy. Forget Mr. Khan.